Hello everyone, may the 4th be with you. I'm Mr. John here from Areteem Institute with this week's Thursday Tidbit, where we're going to be talking about roller coaster physics a little bit, giving an introduction to energy. Now, what is the inspiration for this? What is the inspiration for the greeting we got today? Well, this Saturday we are going to be participating in the STEAM Science Strikes Back event. It's a Star Wars themed event, right? Not held on May the 4th, but a little bit after that there. And our Carnival booth is going to be featured in the Hyperspace Hall of Steam at that event. One of our top hits at the booth, we have some fun math games, different things you can try out at the booth, but we always also include a VR roller coaster there as well. And right, in this video, we're going to talk a little bit about potential kinetic energy and see how that's a great way to understand some of the speeds or velocities in the physics term for roller coasters. And when you're designing roller coasters, these are things you could keep in mind as well. Now, going back in history, we have the famous story, true or not, about Newton understanding gravity or thinking about this idea of gravity as a force when he's watching an apple fall from a tree. You can do a lot of physics there, right? We're not going to dive too deep into that physics stuff today, right? Talking about the force of the apple, what's its acceleration, all of those things can be done. But we're going to take and think about things more in terms of energy today. So, right, this speed of an object falling, right, or going on a roller coaster in terms of that energy there as well. So what are the two kinds of energy that are going to be the main focus today? Right, first of all, we have kinetic energy. This is an energy, Ke, that measures an object in motion. So, right, an object in motion has some energy. That energy is given by this equation, 1/2 mv squared. M is the mass, v is the velocity. We're not going to worry too much about units in this video or next week's follow-up video, right? M should be in kilograms, velocity in meters per second, right? Then that gives you the kinetic energy in the correct units. We're not doing too much of the physics there. Want to focus more on the math portion. That is in contrast to this idea of potential energy. So kinetic energy, motion, right? Potential energy is the kind of energy that can be converted. And that can be, right, could happen in different ways there. Of course, if we're talking about gravity and objects falling, right, as an object falls, then, right, that potential energy is converted into kinetic energy there. For gravity, mgh, using our meters in seconds, right, g in this equation is meters per second squared, right, mass, and then we have the height there that the object is falling as well. Now, let's go back to this apple and do a quick, easy question with this as well. So suppose we have an apple that falls 3 meters. So our kind of setup here, we have some 3 meters. Maybe it's falling off of a tree, maybe not, doesn't matter whatsoever in terms of our physics problem there. Right, we have that apple starting, falling at the top. So one thing that's kind of important to keep in mind here and that we want to be thinking about, right, at the beginning it's, right, stopped. So it's not moving at the top position there at all. And so then it's going to be accelerating. Its speed is going to be kind of something at the bottom. So our question here is, what is the speed of this apple as it reaches the bottom, as it hits the ground there. So the idea here, right, and this is just kind of our initial version of this. I'll let you think about other complications you might have here. At the top, what can we say about the potential energy of this apple? So this potential energy of the apple is the mass of the apple times our g times our h. Now let me just leave the g in there for a second. Right, the mass we don't know, so this is going to be 3 for the height, and then we have m and then g in that scenario. Now, at the bottom, right, let's think about the kinetic energy, because remember, we're trying to find the speed of the apple. So the kinetic energy here is 1/2 mv squared, and that's what we're looking for in this scenario. Now, the key idea here and the importance about energy and some of the downfalls, which we'll explain a little bit there as well. And I'll leave this up for now, but assume that the kinetic energy is equal to the potential energy. Now, you'll explore in one of the questions I have you thinking about for next week why that's not totally the case. But for the most part, this is true. Roughly speaking, when the apple falls, all of the potential energy turns into kinetic energy, and that allows us to actually have a pretty nice equation for things here. So, first of all, one thing you notice is that me not giving you the mass of the apple actually didn't matter. That mass of the apple cancels out on both sides there. Now this equation is pretty easy to solve, right? Let me just, well, I guess we can write it out here. V squared is going to be 6g for the most part, right? Now this, as an approximation, right? G is 9.81. That's a little less than 10. So this is something a little less than 60 in that scenario, right? If we take the square root, you can approximate this, right? In your head, you should be able to say, this is probably pretty close to 8, or it's somewhere between 7 and 8, probably a little bit closer to 8. We could, of course, use a calculator or think about this a little bit more, but this velocity is going to be 7.67 meters per second in this scenario. So we can kind of find that apple falling, right, and see what happens from there using this energy in this scenario. Now, one thing, right, as we introduce these roller coaster problems for you to think about for next week, one thing I want to keep in mind is that potential energy is relative. It's probably better to think about, right, potential energy as a change in potential energy. How much potential energy is converted to kinetic energy in that scenario? For example, if I'm in my room and I drop a ball from 3 meters to hit the floor, right, it should match the calculations we just did for the apple, at least roughly. Now, does it matter if I'm on the ground floor of a house or the second floor or the 10th floor? No, right? All that matters is that 3 meters that the apple is falling, right? That's why this potential energy being relative is a better way to think about this. And, right, that is pretty clear when you're thinking about roller coasters too, right? If we're thinking about this potential energy between points for something like this here, right, we might only care, okay, when the roller coaster goes from 1 to 2, right? What is this change in height from 1 to 2? Now, we didn't really mention this, but this can actually be done in a couple of ways too. Well, if we're going from 2 to 3, right, now that change in height there is actually going to be, right, going up. So that should lead to a decrease in potential energy, right? Or, sorry, an increase in potential energy, so a decrease in kinetic energy. And that stuff all works the same way. And you don't really want to say, well, okay, how much potential energy is left since 2 is still maybe not off the ground? Is this roller coaster above sea level, below sea level? Doesn't matter. Potential energy relative to the 2 heights that you are changing there. And then these equations actually allow you to get a pretty good idea of what's going on in some of these roller coasters. So as a question to think about for next time, not too difficult, but suppose we're given heights of these 4 points. So point 1 is at 50 meters, point 2 is at 5 meters there, right? Maybe these don't match perfectly with kind of what we're seeing in the drawing, but that's okay, right? With these numbers, right, choosing them so they're not too bad, fairly nice to work with there, 40, 30 meter heights, right? What are the speeds then of the roller coaster, meters per second, at each of those 4 points, right? And, right, just to get you started on this there, right? For 1, right, we want to assume that the speed is 0 meters per second. We go up to that point, right? It has to be pulled up there. That's one thing to think about. And then we have that 0 meters per second at the top. And then, right, at all of those other points, what are the speeds from there as well? This is like that standard, you get to the top of the roller coaster, it pauses, and then you have your drop from there. Now, little bit of real world messiness to think about. Again, we're not going to get into the physics too much, but in fact, the speeds at points 2, 3, and 4 you calculated would actually be lower in real life. If the speed is lower, what does that tell us about the kinetic energy compared to what you might have seen there? And try to think a little bit about what might explain that change in kinetic energy. Why is that kinetic energy higher or lower than you might expect there? This gets into some of the assumptions we're making about converting potential energy to kinetic energy, and we can talk about that quick in next week's video as well. For now, thank you for watching, right? Try that question there, question 1 and 2, right? The follow-up as well. Let us know if you have questions, comments in the box below, right? If you like this video, give us that thumbs up, subscribe to our channel. It really helps us out. And I hope to see some of you this weekend at our event or in the future at a different one of our Steam Carnival events there as well. Goodbye.